So we continue with the Lagrangian mechanics and action principle. Then we go into Hamiltonian mechanics, Poisson brackets, and symplectic propagators. And the end result was just that demonstration I showed you. So we start with the action principle. So classical dynamics is given by stationary point of the action functional, and then action functional is a functional of which is a functional of the particle's trajectories. And this action functional is given with some Lagrangian, and the Lagrangian will depend on the position of the particle at some time t and its time derivative in some time t. And then so now it's sort of very important to remember that what this is. So this S is a functional, meaning that it takes function as an input. So we supply some function and then we ask, is this the stationary point? So if you do some variation to this function, does it change? So stationary point of an action functional. So stationary point means that the variation of the functional is 0. And then this L depends locally on the trajectory and its time derivative. And you can see that it's not independent. So if we vary the position q in some time t 0, then we also modify the time derivatives before and after that. So these are not independent, but in terms of this function L, so this function L has just two arguments, a and b, and this is the function L itself is not independent. So we'll end up with some partial derivatives. So one needs to be a little bit careful about that. So we will now try to calculate the variation. So we have the delta S, and we can write the delta S in such a way that we actually use some delta Qt here to vary it. And now we need to substitute this function S here. So we have substituted here the delta Q, and here we actually have dot of delta Q. And then we need to subtract the function again, like so. And now we need to expand. So we can see that now we are having variation of this L with respect to its first argument and second argument. And now we can expand this as a Taylor series. And there we need the partial derivatives of L, so we can expand it. So let's do that next. So we have this thing here, and then we can write this this thing here in such a way that it's actually the old L dot Qt, and then we need the partial derivative of L with respect to its first argument. Now this is where I warned you that one should not confuse this partial Qt and partial dot Qt. It has only something to do with how you defined L. So if you get confused, you should think L with two arguments, a and b, and then write L with this a and b, and then take these derivatives. I'm only explaining this because this is where I had confusion when I was a student. So now we have take the partial derivative of L with respect to its first argument, and then with respect to its second argument. So I think I have now, one moment for the latex to be complete. So let's see how it looks like. Did I do it correctly? So there's one extra L over there. So I have this variation here, and then I have Taylor expanded the L in such way that it's L, Q, and Q dot. Then I have taken partial derivative of L with respect to its first argument and with this variation of it, and partial derivative of L with respect to its second argument and variation of that, and subtracting that one, and this one will just cancel that one. So we will end up, I will just, in the second row, I will cancel this part with this part. And now it's still very non-trivial because we have variation of Q dot. So dot implicating time derivative. I will write it explicitly as so. And now we can do partial integration. So we have time derivative of something here. So I can do partial integration of that one. So just first, I will take, so this was the first term, and I will take that as such. And then how you do partial integration, it's minus. And then we are taking dot of this side. So now we will take dot of that side. So we have like d dt of this one instead of this one. And a boundary term of some sort. I will just say boundary. So because it's important in some cases, but not right now. So now we see we have delta Q and delta Q. So delta Q is arbitrary so it needs to be stationary with respect to all variations. So we actually can conclude that this equation must hold always. So we have now derived Taylor Lagrangian equation. So I will just make the Lagrange equation here, so we can remove the integration and variation, like so, and this needs to be 0, like so. So let's now derive the equations of motion for the harmonic oscillator. So the Lagrangian of the harmonic oscillator, it will be T minus V. So it will be the kinetic energy will be mv squared. So it will be m dot q squared. So we remember that L depends on q and dot q. And then minus, then it will be m times m times omega squared q squared. And then we can conclude for the Euler-Lagrange equation. So if we take variation of this, the Euler-Lagrange equation yields, so first with respect to q, so we will have second derivative of q, so it cancels this one, so we have m omega squared q, and that's with the minus. And then we have the partial derivative with q dot, and that will be m q dot. And then we have the minus and the second derivative of that one. So minus, and so we have the double dot of that one. And then we can a little bit reshape this equation. So so let's divide it with m, and let's move this term to the right hand side. So it was with minus, so it will go to plus, and then let's put this minus here. So, and for example, we can solve this using phasors. So we substitute something like e power I omega t. So I will just put prime here, so we don't yet know that it will oscillate in frequency omega. So then we like this one, we take second derivative of this one. So we actually get I omega primed squared over here when we take that one. And then we have minus omega squared of that one. And then we have I squared, that's minus, so it's that one. So resulting into omega prime equals omega. So we'll get stationary oscillation in the frequency of the harmonic oscillator, which is determined by its stiffness and its mass. Okay. So that's the basics of Lagrangian mechanics. And then we move on into Hamiltonian mechanics.